Hello everybody. Today we're going to have a look at arithmetic sequences and series and see if we can figure out how we can use them from problem solving. So let's start with some definitions and then we'll work from there. A sequence of numbers describes a pattern. So in this case, our first sequence, we have 1, 1, 2, 3, 5, 8. That's the Fibonacci sequence. And the pattern is just that it adds the previous two numbers. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 2 plus 3, so on and so forth. So the next sequence, 1, 2, 4, 8, 16. Well, the pattern's obviously it doubles each time. 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, so on and so forth. The next pattern is the even numbers, starting with 2, 2, 4, 6, 8, 10, increasing by 2 each time. The next pattern is the odd numbers, again, 1, 3, 5, 7, but increasing by 2. And the next one is the counting numbers, 1, 2, 3, 4, 5, 6, 7, increasing by 1. By definition, we call each number in our sequence a term. So using 1, 2, 4, 8, 16, the first term is 1, the second term is 2, the third term is 4. And then we have the sequence that we're looking at today. So the first one will be the arithmetic sequence family, and that's where the difference between two adjacent numbers is constant. So if you look here at 1, 2, 4, 8, 16, the difference between 1 and 2 is 1, between 2 and 4 is 2, between 4 and 8 is 4. The difference is not the same. It changes depending on your position in the sequence. Whereas for even numbers, odd numbers, and the counting numbers, they go up by 2 each time, this goes up by 2 each time, this goes up by 1 each time. The difference is the same from term to term. So we would say 2, 4, 6, 8, 10, for instance, has a constant difference of 2. As each consecutive number increases by 2, it is an arithmetic sequence. 2, 4, 8, 16 is not an arithmetic sequence, as the difference between consecutive numbers between 2 and 4, 4 and 8, 8 and 16 is not constant. Here it's 2, here it's 4, here it's 8. Let's have a look at an arithmetic sequence. So here's a pattern. We are having matchsticks made into boxes. The first box has 4 matchsticks, 2 boxes would have 7 matchsticks, 3 boxes would have 10 matchsticks, 4 boxes would have 13, and if I did the next one in the sequence, we start with 1, then we add on, oops, that's not very well done, 3 more matchsticks to make 2 boxes, 3 more matchsticks to make 3 boxes, 3 more matchsticks to make 4 boxes, and 3 more matchsticks to make 5 boxes. And we can put this in a table. We start with 1 box, then we add 3 matchsticks to make 2 boxes, which would be 7 matchsticks in total. Then for the third position in the sequence, the third term, we would have our original 4 matchsticks plus 2 lots of 3. For our fourth position in the sequence, we would have our original plus 3 lots of 3. For the fifth position in our sequence, we would have 4 plus 4 lots of 3, so 4 plus 12 would be 16, which is what's written in the table. And we can find the number of matchsticks for any position in the sequence by multiplying the position number by 3 and adding 1. 3 times the first position would be 3 plus 1 is 4. 3 times the second position would be 6 plus 1 would be 7, and so on and so forth. Or we could look at it a little bit differently. We could say we started with 4 matchsticks, and then we did n take 1, so that's 1 lot of 3 for the second position, 2 lots of 3 for the third position, 3 lots of 3 for the fourth position. That's why we take away 1 from the position number. So if we look at that number and this one, there are always 1 less. And then times it by the difference. So each time we are adding on 3 more matches. Funnily enough, this simplifies to that if you multiply it out. And we can use some algebraic notation to show this. T1 is just the first number in the sequence, and for T2 we're just going to add on 1 lot of the difference. In this case it was 3. For T3 we're going to add on 2 lots of the difference. For T4 we're going to add on 3 lots of the difference. For T5 we'll add on 4 lots of the difference. And for Tn, the nth term in any sequence, we will subtract 1 from n add that to the original term, and then multiply that in take 1 by d, which is what happens here. Now, what happens though if we didn't want to just find the term in the sequence? We wanted to find out how many matchsticks we'd need to do all the shapes up to a position in the sequence. So if we just wanted S1, the sum of the first n values in our sequence, it would just be 4. But if we wanted the sum of the first 2 shapes in our sequence, it would be 4 plus 7 is 11 matchsticks needed to make this and this. If we wanted to make all 3, we would need 10 plus 7 plus 4 is 21. And I suppose the big question now is, what if we wanted the 50th? So 50 plus 49 plus 48 plus 47 terms in the sequence. We don't really want to work out all of the terms up to that point, so we're looking for some sort of algebraic solution to help us, and there is one. So the sum of the first term would just be t1. The sum of the first 2 terms would be t1 plus t1 plus t, which we found out from before. And if we added these together, that would give us 2t1 plus t. For the first 3 terms would be t1 plus t1 plus d plus t1 plus 2d, which would give us 3t1 plus 3d. 1, 2, 3t1 plus d plus 2d is 3d. And so on and so forth. And if we look at this, it's a bit hard to see a pattern on first observation. There's no real connection between the term number or the sequence, the series number, and the formula. Other than this first one, it seems to be increasing by 1 and is the same number as the sum, but these are doing something weird. So, whilst it's not obvious, there is actually a pattern there, and it is quite a nifty way of finding out what the formula is. You write it out in full. Here's the sum here. First term plus the second term plus the third term to the nth term. And then you write it backwards. So this is the nth term minus the n take 1th term all the way down to the first term. And you add them together. So t1, so the sum of this list plus the sum of this list would just be 2 times the sum of all the numbers in the sequence. Take the first term and the last term, add them together, and you get 2t1 plus n take 1d, which is this here. And then if you do that for the second term and the second last term, funnily enough, you also get 2t1 plus n take 1d. And if you do it for the third and the third last term, you also get 2t1 plus n take 1d, which gives you n lots of 2t1 plus n take 1d is equal to 2 times the sum of the series. Series is what we call adding up consecutive terms in a sequence. If we divide both sides by 2, we get Sn equals half n 2t1 plus n take 1d, and this is the formula for finding out the sum of n values in a series. And here's the first 6 terms written out so that you can see that the formula works. Let's do an example. So let's use it. So we're going to use this formula up here to solve this problem here. Find the sum of the first 10 odd numbers. So it would be S10, the 10th number in a series. The first term would be 1, that's the first odd number, and it's going to increase by 2 each time to get to the rest of the sequence. So a half of n, which would be a half of 10, times by 2 times the first term, 2 times the first term, 2 times 1, plus n take 1, well n is 10, 10 take 1 would give us 9, and then multiply that by the difference, which in our case is 2. So simplifying this down a bit, half of 10 is 5, 2 plus 9 take 1, 10 take 1 is 9, times 2 is 18, so 5 times 2 plus 18, 5 times 20 would give us 100, which sounds a bit high, but when you actually look at it, it's quite obvious that it is 100. Here's a list of the first 10 odd numbers. If we look at the first and last one, 1 plus 19 adds to 20, 3 plus 17 adds to 20, 5 plus 15 adds to 20, 7 plus 13 adds to 20, and 9 plus 11 adds to 20, which logically just means it's 5 times 20, which is 100, which is what our series formula found out for us. So there you go. We've had a quick look at how to find terms in an arithmetic sequence and how to how to find the nth term in an arithmetic sequence, and how to sum the first n terms in an arithmetic sequence to find the series value. And we can now use that to solve the AMC problems that I've set during the week. So I hope that was helpful, everyone, and I'll see you on Tuesday.